Hello everyone, welcome back to Math with Allison. Today we're working in our sequences and series, so we're going to be talking about the alternating harmonic series. So let's go ahead and dive into it. First we have the harmonic series. That is the summation k equals 1 to infinity of just 1 over k. So if we were to write this out, we would have 1 plus 1 half plus 1 third plus 1 fourth, right? And this is going on forever. Now the alternating harmonic series is where we add in an alternating -1. So this is going to be equal to 1 minus 1 half plus 1 third minus 1 fourth, so on and so forth, right? So the idea is we know that the harmonic series diverges, but what does the alternating harmonic series do? Let's take a look at their sequences, right? So as a sequence, let's go ahead and think about 1 over k first, right? This is going to be k equals 1 to infinity. So if I were to plug in 1, I would just go up to the value of 1, right? This is going to be my k value, or n value if you have 1 over n, right? When we plug in k is equal to 2, we get 1 half, then we get 1 third, right? 1 fourth, 1 fifth, and 1 sixth. The alternating harmonic series looks a bit different. We start at positive 1, and then we go down to negative 1 half, positive 1 third, negative 1 fourth, positive 1 fifth, negative 1 sixth, right? So both of these are converging. They're both converging to 0, right? Both of these going to 0, but that doesn't help us with a series. So let's go ahead and think of this as a series. We're going to go ahead and take the partial sums, right? So if we have s sub 1 of our harmonic series, that's just going to be equal to 1. So I'm going to go ahead and plot that first one. We have a value of 1. Now, if we get our next partial series, we get 1 plus 1 half. So what we're doing is we're adding on each time, right? So we're going to go up an additional 1 half, right? To get our third partial sum, now we're going to add an additional 1 third. When we go to the fourth partial sum, now we're adding 1 fourth, right? Then we're adding 1 fifth, and you can see that we're forever adding. So we have something in terms of the partial sums that is just going to be increasing and increasing, right? Now let's see the difference with the alternating harmonic series. Of course, our first partial sum is going to be equal to 1, right? But then what we do is we take 1 minus 1 half. So what happens is we bounce down, we subtract 1 half. But what do we do next? We add 1 third. So here what I do is I add 1 third, then I subtract a fourth, right, in order to get that next one, and then we add a fifth, and then again we are subtracting a sixth. And notice what's happening right here. It's doing something like this, right, where all of those little spaces are getting smaller and smaller in between, and it looks like we're actually converging to a number, right? So what test we're going to actually use is the alternating series test. So the first thing we need is that our a sub k terms are non-increasing. So in this case, our a sub k is just going to be 1 over k, right? We need to show that these are decreasing or non-increasing. You can do that by thinking of it as a function. So here we have f prime of x is equal to negative 1 over x squared, right? This is going to show if the function is increasing or decreasing. So we do have a critical value, right? X cannot be equal to 0, but that's okay because our index is starting at 1 going on to infinity, right? So we don't have to worry about that. And I also know that this first derivative is going to be less than 0 for all values x greater than or equal to 1, right? And that's because it's negative. When the first derivative is negative, the function is decreasing. So by using this as a function, we have that a sub k is decreasing for k values greater than or equal to 1, right? So you can think of it as a function. It's like you're using the first derivative test. That's one way to prove it. I'm sure there are other ways, but I like that way. So since we have that they're non-increasing or decreasing, right, we can now look at the limit. So we want the limit as k goes to infinity of 1 over k to equal 0. And that is, of course, true, right? As k grows infinite, 1 over k goes to 0. Since both of these conditions are met, that means it's going to converge. And that's how we can show that even though the harmonic series diverges, the alternating harmonic series converges, which is super cool. So that's all I have for us in this video today. If you enjoyed it, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.